For decades, the most successful theories in physics have been mathematically incomplete. To describe the fundamental properties of matter, standard physics resorts to a technique called renormalization, to skip steps and hide mathematical infinities, a method criticized by pioneers like Richard Feynman. This compromise means these theories can only explain approximately 1 to 5% of the proton's mass, the particle that makes up 99% of everything you see. But what if those discarded infinities were the key? In their paper, The Origin of Mass and the Nature of Gravity, physicists Nassim Haramein, Cyprien Guermont-Prez, and Olivier Alirol reveal the shocking truth. The tremendous pressure of empty space itself, zero-point energy, is the source of the proton's mass and structure. And in doing so, they demonstrate that this geometric mechanism unifies the intense, strong nuclear force and gravity into a single cosmic geometry.
Okay, let's unpack this. Imagine the empty space right in front of you. What if that space isn't empty at all? What if it's the incredibly energetic, bustling source of everything you see, everything you touch, even the very stuff you're made of, including your own mass, and the gravity that keeps your feet firmly on the ground?
It's a question that flies in the face of our everyday experience, doesn't it? We perceive space as passive, just a void.
Right, just nothing.
But physics, particularly quantum physics, paints a much different, far more active picture.
And today, we are taking a deep dive into a fascinating source that suggests exactly that radical idea. This paper presents a really comprehensive analytical solution proposing that mass and gravity aren't fundamental properties or separate forces, but might actually emerge from the energy of the quantum vacuum itself.
Yeah, it's an ambitious attempt to connect the dots between, the subatomic world and the cosmic scale, using the vacuum as the unifying principle. A pretty big claim.
It really is. So our mission in this deep dive is to guide you through the complex ideas in this paper. We're going to try and simplify the concepts, connect them into a compelling narrative, and explore the surprising, often mind-bending conclusions the authors reach.
Yeah, hopefully give you some serious aha moments.
Exactly. And maybe even a reason to chuckle at the sheer audacity of it all. We'll start with the big foundational ideas and then zoom in on the specific, intriguing details from the source.
So prepare for a journey, really, from the smallest theoretical flicker of energy all the way up to the gravitational pull of the entire universe.
If that sounds like your kind of trip, make sure you like and subscribe so you don't miss any future episodes.
All right, are you ready to potentially see reality a little differently?
Let's do it.
Let's jump into the vacuum. Okay, so let's challenge that idea of emptiness right away. Because the starting point for this paper, and for a lot of quantum physics really, is the concept of the quantum vacuum. Not as a void, but as a dynamic, energetic field.
It's like saying the quietest room you can imagine isn't actually silent, but filled with invisible noise you just can't normally hear. Is that kind of the idea?
That's a great analogy, exactly. And this idea isn't new either. The paper traces it back over a century to Max Planck's early work on thermodynamics and black body radiation.
Black body radiation, studying how objects emit light based on their temperature, right?
That's it. Planck, the father of quantum theory.
So how did he find energy in emptiness? That seems like the big first step.
Well, in his mathematical derivation for the spectrum of light emitted by a perfect absorber, a black body, he found something unexpected. Even at absolute zero temperature, when theoretically all motion should stop.
Right, 0 Kelvin, everything's frozen.
His equations predicted a non-zero expectation value for the electromagnetic field's energy density. There was still energy there.
Wait, energy at absolute zero?
This is what we now call zero-point energy, or ZPE. Energy that exists even when things are supposedly as cold and still as they can possibly get.
Zero energy at zero temperature. That sounds contradictory.
It does, doesn't it? But it comes from the fundamental nature of quantum oscillators. You have to think of the electromagnetic field as being made up of countless tiny oscillators, like little vibrating things, one for every possible frequency and point in space.
Okay.
And in quantum mechanics, even the lowest possible energy state for one of these oscillators isn't actually zero. It has a minimum 0-point energy. That's thanks to the Heisenberg Uncertainty Principle, essentially.
The uncertainty principle. Can't know everything perfectly.
Exactly. So you have this minimum energy for every oscillator. Now, what happens when you try to sum up this minimum energy for all the possible oscillators in the vacuum across all frequencies?
Something tells me the answer isn't small.
Not small is an understatement. You get infinity.
Infinite. Like actually infinite.
A literal mathematical divergence to infinity. The theoretical energy density of the quantum vacuum is predicted to be infinite in every single point of space.
Wow. Okay, so that's obviously been a huge puzzle in physics, right? I mean, we don't see infinite energy exploding out of every point in space.
Definitely a puzzle, a big one. What physicists often do is perform a mathematical trick called normalization or renormalization.
Okay, what's that?
They essentially reset the 0 point for energy calculations. It's kind of like saying, okay, this infinite ground state energy is just the baseline, the sea level. We'll measure all other energies relative to it and just ignore the infinite baseline itself for practical calculations.
Sweeping it under the rug a bit.
Well, it works mathematically for many calculations in quantum field theory, letting them predict things very accurately. But the authors of this paper argue you can't just ignore it, not if you want a complete picture.
Ah, so they think the ZPE is actually important, not just an artifact.
Precisely. They highlight that, according to their framework, this 0 point energy is absolutely essential for the mathematical consistency of quantum mechanics itself.
How so?
It's what ensures that fundamental quantum operators, like creation and annihilation operators, don't commute, meaning the order you apply them matters. And that non-commutativity is what upholds the Heisenberg Uncertainty Principle.
Yeah. So the fuzziness of quantum reality, the fact that you can't measure, say, position and momentum perfectly at the same time, that fundamental weirdness relies on the vacuum actually having this inherent fluctuating energy.
That's a core argument they make based on the mathematical structure, yeah. The ZPE isn't just some calculational anomaly you can subtract away. It's baked into the dynamic nature of the quantum world. It's real.
Okay, my mind is already stretching a bit. The vacuum is a sea of fluctuating ZPE, theoretically infinite energy everywhere. That's a wild starting point. But how on earth do you get something solid, something with mass, like a proton, out of that? That feels like going from an abstract ocean of energy to building a concrete house from water ripples. Seems impossible.
And this is where the paper gets genuinely revolutionary, I think. They pivot from this general, almost philosophical concept of ZPE to a very specific, tangible outcome. The mass of a fundamental particle, the proton.
The proton. Okay, solid ground, relatively speaking. A core building block of every atom makes up the nucleus with neutrons. It's got very specific measured properties, including its mass. We know that number very well.
Exactly. And their central, really mind-blowing claim is that their detailed computations demonstrate the coherent modes of these quantum vacuum fluctuations.
Coherent modes, like organized fluctuations.
Yeah, exactly. Fluctuations that are somehow in sync, resonating.
Yeah.
Specifically, they argue that these coherent modes resonating at the characteristic timescale or frequency of the proton directly result in the emergence of its mass.
Whoa, hold on. Coherent modes resonating. So the vacuum isn't just random static noise everywhere. At the scale of a proton, the vacuum energy is somehow organizing itself, vibrating in a structured way. And that organized vibration is the proton's mass.
That's the picture they're painting. Think of it like music. Random noise has energy, sure. But organized sound, music, has structure and specific frequencies, patterns.
Okay, I like that analogy.
They're suggesting that at the proton scale, the vacuum energy isn't just random noise. It's like a specific note being played, a fundamental resonance. And that resonance manifests as the mass. The vacuum isn't just the space around the proton. It's the very source field from which the proton's energy, its mass, emerges.
Wow. The vacuum is actively creating mass through resonance at certain scales. That's a totally different picture than thinking of mass as just an inherent property of the proton. And they can calculate this. They actually get a number.
Yes, they perform a calculation based on these vacuum fluctuations at the proton scale. And they state that the calculated energy density value they get is consistent with the energy density found in a tiny Casimir cavity of the same characteristic size.
Ah, the Casimir effect. I remember that. That's where two uncharged metal plates placed really close together in a vacuum get pushed towards each other, right?
Exactly. Because the vacuum fluctuations outside the plates are different from the ones between the plates, creating a net pressure.
So the Casimir effect is experimental proof that the vacuum has real physical energy that can exert force when you constrain it somehow.
Precisely. So the author is essentially saying the intense vacuum energy density they calculate as the source of the proton's mass matches the kind of energy density you'd find trapped in a Casimir-like space the size of a proton. It links their theoretical calculation to a known, experimentally verified phenomenon involving vacuum energy.
Okay, that's a pretty cool connection. So vacuum resonance creates the proton's mass energy, consistent with Casimir physics. But how does this relate to the structure of spacetime? to gravity. I mean, that's the other half of their paper title, and perhaps the biggest leap of all.
Right, this is where their specific analytical solution comes into play. They describe the structure of quantum spacetime itself, not as a passive grid, like graph paper, but as a dynamic network of these very vacuum fluctuations.
So space and time aren't just the stage where things happen, they are the fluctuating energy field. The stage is the actor.
In their view, yes, the very fabric of reality is this constantly dancing field of energy. And within this fluctuating spacetime, they propose something they call a screening mechanism.
Like filtering something.
Kind of. Imagine that theoretically infinite vacuum energy we talked about earlier. They suggest that at specific physical scales, this immense energy is screened or filtered or maybe organized in a way that defines physical reality at that scale. It's like looking at blinding light through different types of sunglasses. Each filter reveals a different aspect or structure of what's there.
Okay, a screening mechanism that organizes or filters the vacuum energy at certain scales. Makes sense conceptually. Where does the first screening happen in their model?
The paper identifies a crucial first screening occurring at a really fundamental quantum scale related to the proton. It's reduced Compton wavelength.
The reduced Compton wavelength. Okay, remind me. Give us a simple picture of that scale. What does that represent?
Think of it as a particle's fundamental length scale in quantum mechanics, intrinsically linked to its mass. For a proton, it's an incredibly, incredibly tiny distance, much, much smaller than the proton's measured size, like its radius. It's a scale deep inside the proton where purely quantum effects are totally dominant.
Got it. Super tiny, deep quantum scale inside the proton. So at this scale, the vacuum energy undergoes this first screening. And the result, what does this filter reveal?
Okay, this is where you might need to hold on to your hat. According to the paper, this first screening reveals a mathematical structure with a direct relation to Einstein's field equations.
Einstein's field equations. The ones that describe gravity. General relativity.
Very same. And specifically, it relates to the Schwarzschild solution to those equations.
Wait a minute. The Schwarzschild solution, isn't that the mathematical description of the gravitational field around a non-rotating spherical mass? Like a black hole.
It is. That's exactly what it describes.
You're saying that inside a proton, at this tiny quantum scale, the screened vacuum energy takes on a structure that looks like the math for a black hole's gravity.
That's what the paper claims, yes. They state that this screening process, applied at the proton's reduced Compton wavelength, defines what they call a source term for the internal energy of the proton. And this energy, emerging directly from those zero-point vacuum fluctuations, has the mathematical form of a gravitational source, specifically one described by the Schwarzschild solution at this fundamental scale.
So the structure that emerges from the vacuum energy at the proton's deepest quantum level, it looks mathematically like the structure of a mini gravitational source, like a tiny quantum black hole-like core made of vacuum energy. My brain just did a little flip-flop there.
It's an astonishing implication, isn't it?
Right.
That's the consequence of their finding at this first screening level. They're connecting the fundamental structure derived from vacuum fluctuations inside a particle directly to the mathematics of gravity usually applied to colossal objects like stars and black holes.
Okay. Deep breaths. First screening at the Compton wavelength gives us this wild result about a gravitational core-like structure born from vacuum energy. Where does the actual measurable mass of the proton come into the picture? The number we actually measure in labs.
That emerges from a second screening mechanism, according to their model. This one happens at a different scale, larger than the Compton wavelength, but still incredibly tiny. The proton's measured charge radius.
The charge radius, okay. That's the size we typically measure when we probe the proton with electrons, right? Kind of its fuzzy edge where the charge is spread out.
Exactly. It's the scale associated with its electromagnetic interaction, the extent of its positive charge. And according to the authors, when the vacuum energy undergoes this second screening at the proton's charge radius, the result accurately matches the proton's measured rest mass.
Okay, stop. Let me get this straight. First screening gives the internal gravity-like structure. Second screening at the charge radius gives the actual mass value we measure.
That's the claim. This is the second specific quantitative connection they make. Vacuum fluctuations, screened at a particular scale, the charge radius, yielding the precise value of the proton's mass.
So first, the coherent modes create the energy density consistent with Casimir physics. Then the screening mechanisms organize that energy, revealing an internal gravity-like structure at one scale and defining the measurable rest mass at another scale. This is intricate. What else did they find? There must be more.
Oh, there is. Building on that finding of an internal gravitational-like structure, the one related to Schwarzschild geometry that emerged after the first screening.
Yeah, the mini black hole-like core thingy.
Right. They decided to compute its theoretical Hawking radiation value.
Stephen Hawking's idea, right? The theoretical energy that black holes are supposed to slowly leak out due to quantum effects near their event horizon. Another concept straight out of black hole physics.
The very same. They took the formula for Hawking radiation and applied it to the tiny, dense, Schwarzschild-like core structure they identified within the proton, using their vacuum fluctuation model.
Oh, okay. Applying Hawking radiation math to something inside a proton. That sounds bold. And the result, did they get like some tiny theoretical energy value?
They got a value, yes. And here's the kicker. This calculated Hawking radiation value is found to be equivalent to the rest mass energy diffusing within the internal structure of the proton.
Equivalent to the... Wait, stop it. You're telling me the energy theoretically radiating from this tiny, dense, internal gravitational structure they found matches the energy that is the proton's rest mass.
That's the remarkable finding they present in the paper.
So it's like proton's mass is the glow or the leakage, the Hawking radiation coming from its own vacuum energy-fueled gravity-like core.
That's the implication, yes. It draws this almost unbelievable direct line between concepts typically reserved for astrophysics and black holes. Schwarzschild geometry, Hawking radiation, and the internal dynamics and the very mass of an elementary particle like the proton, all originating, they argue, from these fundamental vacuum fluctuations.
My mind is officially blown. Okay, so we've linked vacuum energy to mass and gravity, even black hole physics, right inside the proton structure. What about the other fundamental forces, specifically the super strong ones that hold atoms and nuclei together? Where do they fit in?
Good question. Their model extends to those too. Based on the vacuum fluctuation structure they describe inside the proton, this dynamic energetic core, they were able to calculate the pressure gradient arising from these fluctuations.
Pressure gradient, like how the pressure changes as you move outwards from the center.
Exactly. Think of it as calculating how the internal pressure created by all that vibrating vacuum energy changes from the center of the proton outwards towards its edge. And as you know, a change in pressure, a gradient, creates a force.
Right, like air pressure differences create wind. So the vacuum energy vibrating inside the proton generates internal pressure forces.
That's the idea. And when they calculated these pressure forces stemming from their vacuum model, they found they were a very good fit to the measured values of the color force and the residual strong force.
The color force and the residual strong force. Hang on, those are the big ones, the titans of the subatomic world, aren't they?
They absolutely are. The color force is what binds quarks together inside protons and neutrons. It's mediated by gluons, and it's incredibly strong, often visualized as energy flux tubes stretching between quarks, making it impossible to pull them apart individually.
For confinement, right.
Exactly. And the residual strong force is the leftover effect of that color force that leaks out, effectively gluing protons and neutrons together within the atomic nucleus. Again, immensely powerful, but very short range. These forces are usually considered completely distinct from gravity or electromagnetism.
And this paper is saying the pressure generated by the vacuum fluctuations inside the proton, calculated from their model, actually matches the strength of these incredibly strong forces.
That is their claim, yes. A very good fit, they state. And this finding leads directly to their major unification proposition.
Ah, unification. The dream of physics.
Indeed. They state that this framework, where mass and these forces arise from vacuum fluctuations, allows them to unify all confining forces, meaning the color force keeping quarks bound and the residual strong force keeping nuclei bound with the gravitational force.
Unifying the strong force with gravity. Okay, that's the physics equivalent of finding the Holy Grail, Bigfoot, and a working warp drive all in the same afternoon. I mean, that's huge, if true.
It's a monumental goal in physics, absolutely. Trying to find a common origin for all the fundamental forces. And the mechanism they propose for this unification is really key here.
How do they propose it works? How can gravity and the strong force be the same thing?
In their model, gravity isn't treated as a separate fundamental force acting between distant masses in the usual way. Instead, gravity is shown to be emerging from the curvature of spacetime itself.
Okay, that's standard general relativity.
But that curvature, they argue, is induced by the quantum electromagnetic vacuum fluctuations. The energy density of the vacuum is what warps spacetime.
Ah, okay, so the vacuum's energy density literally warps the fabric of spacetime, and we experience that large-scale warping as gravity. That makes sense within their framework.
Exactly. And then These intense internal forces within particles, the strong forces, are also manifestations of these same vacuum fluctuations and the resulting spacetime curvature, just acting very, very strongly at different, much tinier scales inside the particle.
So gravity is the large-scale, gentle curvature from the vacuum energy, and the strong force is the intense, short-range curvature or pressure from the same vacuum energy, just localized inside particles.
That's the unified picture they are painting. The vacuum isn't just providing the mass, it's the fundamental canvas and the paint. It generates both the forces that hold particles together internally, strong forces, and the force that governs their large-scale gravitational interactions, both stemming ultimately from space-time curvature induced by vacuum energy, just expressed differently at vastly different scales.
This is genuinely mind-bending stuff. They've gone from Planck's vacuum energy to a proton's mass, linked it to black hole physics concepts like Schwarzschild and Hawking radiation, and now claimed a unification of gravity and the strong forces, all originating from this active quantum vacuum.
Does this intricate picture only work for tiny particles like protons? Or does it scale up? Can it explain bigger things?
That's the crucial test, isn't it? Does it work universally? And that's where they broaden their scope significantly. They applied this same quantum vacuum energy density screening mechanism, the same basic idea of filtering the vacuum energy at different scales, not just to a single proton, but to the largest structure we know, the observable universe.
The entire cosmos.
From the smallest fundamental speck, the proton, to the whole cosmic shebang. That's ambitious.
Extremely ambitious. But according to the paper, using this same vacuum fluctuation and screening model applied cosmologically at the scale of the universe, they are able to compute the correct critical energy density typically given for the total mass energy of the universe.
Whoa, the critical energy density. Just remind us, that's the total amount of all stuff, matter, dark energy, the whole inventory required for the universe to have the overall flat geometry that we actually observe, right?
It is, yes. It's a cornerstone value in modern cosmology, derived from observations of the cosmic microwave background and large-scale structure. It tells us the universe's total energy budget, essentially.
And their model, developed by looking inside a proton and using vacuum energy, correctly calculates this huge cosmic number.
That's what they report. The fact that their model, starting from the perspective of a single proton's internal structure derived from vacuum energy, can apparently scale up and accurately predict this immense large-scale cosmological value is presented as, well, pretty strong evidence for the model's potential universality.
It suggests the vacuum really could be the fundamental source of mass and energy across all scales, from subatomic to cosmic.
That's the implication they draw, yes.
Wow. Okay, let's try to quickly synthesize this incredible journey we've been on just to get our heads straight. We started way back with Max Planck predicting this background energy in the vacuum, the ZPE, suggesting empty space isn't empty but is full of this potential.
Right. Potentially infinite potential.
Then the authors of this paper propose a specific mechanism where coherent fluctuations, a kind of resonance of this vacuum energy at the proton scale, actually creates its mass energy with a density that's consistent with the experimentally known Casimir effect.
Linking theory to experiment there. Then they model quantum space-time itself as these vacuum fluctuations, introducing this idea of a screening mechanism where the vacuum energy gets organized or filtered at specific physical scales.
Okay. And the first screening, happening deep inside at the proton's Compton wavelength, reveals an internal structure that's mathematically related to Einstein's gravity equations and the Schwarzschild black hole solution, implying a sort of gravity-like core emerges directly from the vacuum energy.
Yeah, the black hole-proton connection, which is just startling.
Absolutely startling. Then a second screening, happening at the proton's measured charge radius, yields the proton's precise measured rest mass. Another direct calculation from the vacuum model matching reality.
And in an even more astonishing twist, they found the calculated Hawking radiation from that internal Schwarzschild-like core is equivalent to the proton's rest mass energy. So the mass is like the radiation signature of its own internal vacuum-generated structure.
Which connects black hole physics directly to particle mass dynamics in a totally unexpected way.
Right. And it didn't stop there. They showed that the pressure forces generated by this internal vacuum structure match the intense color and residual strong forces holding quarks and nuclei together,
leading them to propose that all these confining forces are actually unified with gravity. Not separate forces, but different scale expressions of the same underlying phenomenon.
Which, in their model, is the curvature of space-time induced by the vacuum energy fluctuations themselves. Gravity is the large-scale curvature. Strong force is the small-scale, intense curvature or pressure.
And finally, this ambitious framework wasn't just limited to particles. They applied the same vacuum energy screening mechanism to the entire observable universe and accurately calculated its total critical energy density, matching cosmological observations.
Suggesting, potentially, a single underlying principle. The quantum vacuum explains phenomena from the smallest subatomic scale, like proton mass and strong force, all the way up to the largest cosmic structures and the energy content of the universe itself.
So the core, the truly mind-bending idea from this paper, if we boil it down, is that mass, gravity, and the forces holding everything together, the very stuff and structure of reality as we know it, aren't inherent properties of particles, nor are they mysterious forces acting across space. Instead, they are presented as emergent phenomena, dynamically arising from the energy, the structure, and the fluctuations of the quantum vacuum.
Yeah.
The emptiness of space, this vibrant field of ZPE, is proposed as the ultimate fundamental stuff of the universe, the source of everything.
And that offers a radically unified perspective, doesn't it? It's an attempt to bridge that long-standing, frustrating gap between quantum mechanics, the world of the very small, and general relativity, the world of gravity and the very large. It suggests a single, potentially elegant origin for seemingly disparate forces and phenomena we observe.
It shifts the whole focus, really, away from thinking about particles and forces as fundamental and towards the dynamic nature of spacetime itself, powered by this underlying vacuum energy.
It really challenges our intuition about what's real and what's empty, doesn't it?
It certainly does. My intuition is definitely feeling challenged right now.
Mine too, exploring these ideas.
Okay, that was an incredibly deep dive into some truly profound, maybe even paradigm-shifting concepts. So here's the final thought to leave you with. If the source of mass, gravity, and the forces binding everything is this vibrant, fluctuating quantum vacuum, this energy-filled emptiness, does that mean what we perceive as solid, unchanging matter is? Well, is it just a highly organized, incredibly stable pattern of waves, ripples, and fluctuations in the very fabric of space-time?
Based on the framework presented in this paper, that's a pretty compelling way to view it, yeah. Matter as organized vacuum energy.
What does it truly mean for our understanding of reality if the space between the stars, between the atoms, and even inside the atoms isn't empty at all, but is the fundamental ingredient, maybe even the source code of the entire universe?
Definitely something to ponder.
Something to ponder long after this deep dive is over. Thank you so much for going on this exploration with us today. It's been fascinating.
And thank you for bringing your curiosity. It's these kinds of questions that push physics forward.